Today, I'd like to welcome Professor Ashe Henry, who is a Robert Noyce Career Development Professor in Mechanical Engineering at MIT. He holds a bachelor's degree from Florida A&M University, and he received his master's degree and PhD from MIT. He started his career with a postdoc at Northwestern and Oak Ridge National Laboratories. He was a fellow in the U.S. Department of Energy before joining the faculty at Georgia Tech. He spent several years at Georgia Tech and in 2018 joined the faculty at MIT. He's working in thermal management and energy transport with an eye on mitigating climate change. Some of you, if you might have noticed that there was an article on the MIT news site featuring his work just posted yesterday. And today he's going to talk to you about technology development in heat transfer and the potential impacts this novel research can have in mitigating climate change. So as he goes through his talk, please enter your questions in the chat. And at the appropriate time, I'll call on you and give you the chance to talk to him yourself. So with that, I will turn it over to you, Professor Henry.
Thank you very much. Before maybe I get started, since you mentioned about appending one thing, I guess, to the introduction, is another thing we're also very heavily involved with in our department is we're doing some new efforts to promote diversity, equity, and inclusion. So I'm also our department's faculty diversity chair. And what that basically means is right now I'm helping to lead a group of faculty, staff, students, all together, working together to develop a strategic action plan for our department. What has happened is, I think throughout the Institute, throughout MIT, there has been an interest in trying to diversify the composition of our community. And, there have been various efforts to think about it, to want to do something, but I think there's been a lack of planning and execution. And so not very many sustainable things have happened. There's some exceptions, but we are trying to take a very focused approach in our department and trying to develop some very specific actionable items and things that we can do that will not just change the composition, which is, diversity, but then also making our community more equitable and more inclusive. And so we have a number of really, I think, interesting and creative ideas that we'll be pursuing over the coming years that will hopefully make a dent in that in a systemic way. One of the things we're most proud of that we have already accomplished is our incoming graduate student class is actually the most diverse on record. So we've made some changes to the way that we did graduate admissions this year and got a much more diverse group of students admitted. And the second thing is that we have managed to get the visiting committee to have diversity, equity, and inclusion as like a standing agenda item going forward. And that's a really big deal because it means that even beyond our current department head, we will have evaluations of our progress on diversity, equity, and inclusion. So it's kind of making it systemic, making it long-lived and something that's permanent, so to speak, and part of the program itself. So I just mentioned that up front just to say, that it's an important aspect of what we do in addition to all the technical work, and that's what I'll spend the majority of the time talking about. Just to give you a flavor, my research, generally, we basically work on two main different categories of things. On the left-hand side is a plot showing the results of a number of studies we've done. We study heat transfer, both the physics of heat transfer and applications of heat transfer. So with regards to the physics of heat transfer, we study the physics of atomic vibration. So heat is ultimately just the energy contained in atoms moving, and how that energy is able to move from one location to another, which is heat transfer, is also interrelated with how the atoms are moving. And so we, in my group, one portion of my group, I would say about a third of my group works on studying atomic motion. We do what are called molecular dynamic simulations, where we actually develop from quantum mechanics expressions and mathematical expressions that describe how different atoms will move inside of different materials, different structures. And in particular, we've been really focused over the last few years on what happens when you join two materials, where you have like one material A and material B, and you make a junction between them. How does the heat move across that junction? And so the physics of a lot of that is actually not very well understood. And so we do one third or so of my group does really just physics research using computational tools to study those materials. And what's shown there in this plot is basically we have some new methodologies we developed that, what's shown on one axis here is experimentally measured thermal conductivity. And what's shown on the vertical axis is our predictions of those thermal conductivities effectively directly from quantum mechanics. And so what you see is agreement, like right along the diagonal, what we predict and what gets measured are very close. And so this is confirmation that our theory is correct. And so that's like, one significant portion of what I do. That's a outgrowth of my PhD research. That's kind of my bread and butter. And once I started being a professor, I branched into a rather new and different area, which is doing macro scale problems, specifically looking at doing heat transfer at extremely high temperatures using liquid metal as a medium, as a heat transfer fluid. There are two technologies that we've been developing. I'll spend the majority of the time talking about the first one, which is thermal batteries, or it's an attempt at solving the grid level storage, grid energy storage problem. And the second technology I'll get to is called methane pyrolysis or methane cracking. It's making hydrogen without making CO2. So I'll try to talk about that briefly. And if there's time, I'll also try to go through a couple slides talking about some of the most important problems that I see as our path to being able to continue to exist on this planet and not die from climate change. These are, I'll point out 5 in particular grand challenge problems that my hope is that the next generation, many of you that are on this call, will take up an interest in these kind of problems and find solutions. These are giant problems, major problems that, if solved, will likely be the linchpin to helping us survive climate change. So let me start with this first problem. I'll spend, like I said, the majority of the time talking about this grid storage problem. So climate change, as far as I'm concerned, is the most important problem in the history of mankind, in the sense that it's the most clear and imminent threat to our species' survival. The other thing about this is, we know what it will take to solve it. We're clear on what has to happen. And one of the most important things that has to happen is we have to decarbonize the electricity grid. So the electricity grid comprises about 25% of the problem. It's where a bunch of CO2 emissions come from. We make electricity by burning fossil fuels, which then drive heat engines, and they make power. And ultimately, what we need to do is we need to do a complete overhaul of the entire power infrastructure. So we need to not use any fossil fuels and replace all of that with renewables. The problem is that with renewables, like solar panels and wind, the problem is you only get the electricity when the sun is out or when the wind is blowing. So the way the physics works is there's no real storage of that energy. And so you just get it whenever the weather is permitting. Now, the problem is the way the grid works is the grid requires, when you turn your light switch on, you expect that power will be available. And the way that works is that people in a room somewhere are actually trying to predict how much power people are going to use in the next hour. And they call up all the power plants and send a message and say, okay, generate this much power because this is how much we're anticipating. And this is kind of how blackouts and brownouts happen, is when they get it wrong, or when there's a failure of some power plants and they're not able to supply enough. And so at the end of the day, we don't really have any storage on the grid. There's no intermediate buffer that holds energy and then gives it to you whenever you want. The energy is dispatched directly from what we think people are going to use. So now if you say, okay, well, I'm going to run the entire grid on renewables, that's a very difficult thing because now it's weather dependent and people's usage of electricity is not necessarily weather dependent. So people expect their electricity, their lights to come on, their heat to come on, regardless of whether the sun is out or the wind happens to be blowing at that instant. And so when you try to think about how are you going to make the grid run completely on renewable energy, you got to have storage. So you got to find a way to take the energy that's available when the sun is out and the wind is blowing, hold it in some form of, I'll just term it a battery. You got to store it somehow. And then when people want electricity, you got to put the electricity on the grid on demand, have it be dispatchable. So what's shown in this plot on the right is a set of curves that basically show so PV penetration is on the horizontal axis. What that means is that's what fraction of the grid's electricity would be coming from solar. This is a hypothetical curve, so it's showing what would happen via simulations of the grid. And what's shown on the vertical axis is how much of that electricity you throw away because you can't use it. And what you see here is that this penetration only goes up to 50%. And what these different curves are different amounts of storage on the grid. And what it shows is that you need a lot of storage in order to be able to utilize the solar energy. Otherwise, you see those curves, tick up to 70%, almost, eventually get to 100%, where you end up throwing away all the solar you have because it's not coming at the time that you need it. So this is the storage problem, and what we're working on is an attempted solution to this. And the main issue, the reason it's not a straightforward solution, is the first thing you would think is, well, let me use maybe lithium-ion batteries or the same batteries they put in Teslas. And the problem is that those batteries are too expensive. They cost too much. If you do solar plus batteries, the batteries cost more than the solar does. And so those batteries are not really well suited for this problem of storing energy at extremely large scales. So what we do is we're proposing and we're working on developing what are called thermal batteries. And a thermal battery, it basically takes in electricity, converts it to heat, my specialty. We store it as heat and then convert it back to electricity whenever people want it. And so it works like a battery, but it's actually really a system of components. It's got two converters. It's got a converter for converting electricity to heat and a different converter for converting heat back to electricity. Now, if when you get older and you take a thermodynamics class, you'll ask this question: why would anyone ever do this? Because this would sound totally stupid if you've taken a thermodynamics class. And the reason it would sound stupid is because we expend great effort to convert heat to electricity the first time. So when we have those heat engines and those turbines that are turning in order to convert heat to electricity, we end up losing the majority of the energy. So the majority of the energy actually gets wasted as waste heat. So let's say you burn some natural gas, you pay a certain amount of money for every joule of energy or every kilowatt hour of energy in that natural gas. And by the time it becomes electricity, you've wasted more than half of it. So more than half of that energy just becomes wasted heat that just gets vented to the environment. And the less than half of it on average ends up becoming electricity. So now you say, well, I'm going to take that electricity, convert it back to heat, and let's do it again. And then when we do it again, we're going to lose half the energy or more again, a second time. So you can imagine you end up throwing away most of the energy. And that's why someone would think this is a very dumb idea. The reason it's smart is because of the cost. So even though you end up throwing away the majority of the energy, storing energy as heat is about 10 to 100 times cheaper than electricity. So even if you take a hit of, let's say, a factor of 2, so it's like half as efficient, it pales in comparison to getting a cost that's 100 times lower. Okay, so that 100 times factor is much more important than the factor of 2 that you pay. So that's the essence of what we're doing. This is generally how it works. The way it works is we take in electricity from renewables, so solar and wind. And what we do with that electricity is we run resistive heaters. So these are, for all intents and purposes, these are giant incandescent light bulb filaments that are very, very hot, so hot they're glowing white hot, just like a light bulb. And What we then do is we pump liquid metal through some pipes past those heaters, and the heaters are converting the electricity to heat. So that's the first conversion. And then the liquid metal is carrying that heat over to this storage unit. And this storage unit is basically a giant bank. I mean, imagine it the size of like half of a football field. It's huge. And it's about 10 meters tall. So it's about 30 feet tall or so. And inside of it are a bunch of giant graphite blocks. So graphite, you can kind of think of it like pencil lead. It's basically carbon. And it happens to be very refractory. It actually does not melt or decompose until extremely high temperatures. But it's very cheap. It's very abundant. Carbon is basically one of the most important elements we're made out of. There's a whole lot of it on Earth. And so therefore we can make this very inexpensively. And we heat up these blocks till they're glowing white hot. And so that's how we charge up the battery, is we take electricity in, we run that heat and move it over to the blocks. And then we have those blocks get heated up to the peak temperature, which is about 2,400 degrees Celsius. I get this phone. All right, sorry about that. So that's how we charge up the thermal battery. And then when we want to, so we hold it inside that storage unit. And then when we want to make electricity, we pump the liquid metal through these blocks, heat the liquid metal back up to the peak temperature, and then send it over to this power conversion unit. And this power conversion unit has inside of it a bunch of pipes, and these graphite pipes here carry the liquid metal. And as the liquid metal goes down through here, the whole infrastructure is glowing white hot, glowing, looks like a bunch of white light coming out of all of this. And what we do is we actually, normally what you would do is you use a turbine to convert heat to electricity, but what we do instead is we actually use photovoltaics. So we actually use a special type of solar panel to convert the heat back to electricity. So we insert, these are actively cooled, so they're sitting on something that's got water cooling on it to keep them cold. And we insert it into that light cavity. And so there's a bunch of light in here, we insert it, and the solar panels, these PV cells, will convert that light to electricity. And that's how we get electricity back out. And a number of reasons why we do this, I'll go over them later when we're in the question and answer period. But that's the basic idea, is we can actually have a very fast response to the grid by inserting those PV cells, and we can move them up and down to actually change how much light they're exposed to, and so we can change dynamically. So this is our main technology called thermal batteries, or sun in the box. The main thing that is compelling about it, the main thing that's compelling about it is the cost. So the cost is extremely low. So the cost of lithium ion batteries right now is about $150 per kilowatt hour. A kilowatt hour is a measure of energy. It's a measure of, you can convert it to joules. And you pay about $150 for every kilowatt hour of energy you could store. And what we expect, or what we have estimated for our technology, is that it gets down below $10. So it's more than 10 times cheaper than batteries are today. It's actually cheaper than any other technology we're aware of. And so for this reason, we're very excited to try and build it and test it out and hopefully get it commercialized so that it's a commercial product you can buy. And so one of the key questions that people usually ask, you probably should ask, is I mentioned pumping liquid metal, and I mentioned temperatures that may sound ridiculously high, over 2,000 degrees Celsius. And that would sound crazy because prior to us doing some work in 2016, there was no pump that could do something like that. And the reason there's no pump is because pumps generally require seals, and the seals are typically made out of polymers. Polymers is a class of materials that is kind of like plastic. So plastic is a polymer. And plastics decompose. The way the molecules are bonded, they are not strong enough to hold themselves together at extremely high temperatures, so they decompose, they'll vaporize, literally turn into gas. And so nobody could make a pump that could go this hot because you don't have any seal. You don't have a way to seal it. And so that was our major step forward in terms of a technological contribution and breakthrough here, is we figured out a different kind of seal. And so we figured out a seal that we can make out of carbon that actually can work as hot as carbon can work. So we can go up to 2000 C or above. And so we demonstrated our first test at 1400 C or 1350 C here shown. This is liquid tin being pumped. Tin is similar to solder. And the reason you can see this, the reason this temperature is actually not as high as we wanted, is because we're looking at it. So when we cut a hole in the insulation so we could see it. And when you see it, a whole bunch of light gets out, and so it cools down. And so we've now done tests where you can't see it, and we measure it a different way, and we've demonstrated up to 2000, above 2000 C pumping. And so this is the main technological contribution we've made. Another more recent technological contribution, just to give you a sense of where we are with this technology and where we're headed, is on those photovoltaic cells. Those are not normal photovoltaic cells. They are a class of photovoltaics called thermal photovoltaics, because you're converting it from a heat source. And the previous record for thermal photovoltaics back in 1980 was 29%. And so over the course of 40 years, just last year, someone set a new world record up at 32%, only went up by a few percent. And but now, just in our lab, we just measured 42%. So we actually pushed it up 10 points. And so we're very excited about this. This is well on our way to our goal. Our goal is 50%. And so if we can get to 50%, then our battery will basically be 50% efficient. And that's actually about as good as I think we can expect. So we're getting closer to our goal. What we're planning to do next with this is build a full system prototype in my lab, and then hoping to start a company and build a 1 megawatt hour pilot, and then eventually scale it up to the gigawatt hour scale. Real briefly, I'll just touch on some other things. It looks like we got about another 5 minutes or so. So once we figured out how to pump liquid metal at extremely high temperatures, it really opened the floodgates to all kinds of new ideas and new concepts, because it was really something that was impossible previously. And one of the other ideas that we're working on is there's another problem, climate change related, which is the way we make hydrogen. So many people may have heard of the hydrogen economy. Even in the absence of the hydrogen economy, you need hydrogen. You need hydrogen because when we use hydrogen to make ammonia, you need ammonia to make fertilizer so you can grow crops and feed 7.5 billion people on Earth. So hydrogen plays a very integral role in the way that we live today. And the way we make hydrogen today predominantly comes from methane, comes from natural gas. So we actually take natural gas and we react it with water. And what that does is that causes the carbon to bond with the oxygen in water, and the hydrogen from the water gets liberated. So you get that hydrogen. You also get the hydrogen that was on the methane. Methane is CH4, it's this molecule here. So you get 2 hydrogens off of the carbon, then you get another 2 hydrogens from the water. That process is called steam methane reforming. It's very well established. The problem is it makes CO2. So the only way we know how to get hydrogen efficiently and cost effectively is to make CO2. So what we're trying to do is develop a new process that doesn't make CO2, but still gives you hydrogen. And the way it works is basically, because now we can go to really high temperatures. If you take methane and you simply heat it up, key point is in the absence of oxygen, right? Like if oxygen is around, it's going to bond with oxygen and make CO2. But if you keep oxygen out of your system and you heat methane up, it actually decomposes into solid carbon and hydrogen. And so you can just cause the molecule to fall apart because it can't survive at sufficiently high temperatures. Turns out that temperature is, attainable. It's not something super high. It's 1400 degrees Celsius, much higher than we can achieve with like a reactor made out of metal, like you would have normally done. But with our new approach of using ceramics and our new seals, we can actually get to 1400 C and cause what's called methane cracking or methane pyrolysis. And so this image shown here is basically a cartoon of the reactor, the way we're building our reactor. What it basically involves is a big container that has liquid tin, and we blow bubbles up through the tin, inside each bubble, you get a little carbon particle that'll form and hydrogen gas, and then the gas goes out the top. And we can recuperate, we can save the energy from the hot hydrogen, we can save the energy from the hot carbon as well. And then we're working on doing separation so you can separate out the carbon in the tin. And the reason this is significant is because the simplest thing you could do would be to take methane, put it in a tube and heat it up. The problem is when you do that and that carbon forms, it's going to form on the walls of the pipe. And very quickly, it'll fill the entire cross section of the pipe and choke the reactor and kill it. And so this approach allows you to actually continually make carbon without plugging the reactor. And so this is a technology we're working on called methane pyrolysis. So with that, I got about a minute left. I'm just going to quickly mention there are 5 major problems. We have a paper in Nature Energy that describes this a bit more. These are 5 thermal energy related problems that are key to mitigating climate change. The first is energy storage. We talked about that. I spent a lot of time talking about energy storage and the grid storage problem. The second one, though, is that is often not really appreciated, has to do with cooling. So the way we make air conditioners and refrigerators today involves chemicals that if they eventually end up getting out into the atmosphere. And when they do, they have a very strong forcing for the climate. And so they are actually thousands of times more problematic than CO2 is. And so even though it's a small amount of the material that's getting out from all the air conditioners and refrigerators around the world, it's actually going to become one of the predominant sources of climate forcing if we don't reinvent how we do cooling. So the way we use cooling is using a process called vapor compression. It's been around for about 100 years, hasn't changed because it works well. The problem is only this issue of these HFCs or hydrofluorocarbons. It's the actual refrigerant that's used. And so we have to reinvent cooling. We have to figure out a new way to make things cold that doesn't involve these molecules or in some way is able to protect them and not actually have them get into the atmosphere. So this is a grand challenge. We don't have any great ideas just yet, but I think many people are trying to come up with things. Another key piece is the industrial sector. So I talked about electricity. We are hopefully likely to switch to electric cars that will then be charged by a decarbonized grid. That's one of the biggest problems that we have. But another big problem is industry. It's almost similar in size to the problem of driving cars. And this problem boils down to a couple major industries: cement, steel, aluminum, and hydrogen. So we're working on the hydrogen problem, but the cement problem is huge. So the way we make buildings makes CO2, and the way we make steel makes CO2. And these are some of the biggest industries on the planet. And we are trying to figure out new ways of doing those things, but we need help. We need a lot of help because there's no solution yet. Another potential problem to be aware of is this, a big source, or let me say a big sink where we use most of our energy is actually in heating and cooling. So we take electricity, which is very high value energy, and then we usually downgrade it to provide space heating and cooling at temperatures really close to what human beings are comfortable with. And so there are a number of ideas for how to just reduce how much energy we use in heating and cooling. And one idea is to, instead of heating up an entire building where you heat up all the air in the building, why not treat it like a local phenomenon like we do with lighting? You don't put light everywhere, you put light just where you need it, where you're actually sitting. And so why not actually locally do heating and cooling? Because you're only trying to cool the person. You don't really care so much about the temperature of everything else in the room. And so this is a kind of conceptual shift, but it's important to think about new inventions and new ways of actually achieving things like this. Maybe you could make it where your clothes are actually doing your space conditioning and it just cools you, the person, rather than all the air around you. So these are important concepts to pursue. The last one I'll mention is long distance transmission of heat. So, we have power lines and those power lines move electricity. They don't move heat. And it's because heat is very difficult to move. But if we could move heat, if someone could invent something so that we can move heat, we have an overabundance of waste heat. I mentioned this when I talked about power plants and how we lose most of the heat. But then we also want to do space heating at our houses and in our buildings. And we have plenty of heat at almost the perfect temperature that we want to use it. We just can't connect the dots. We can't take this heat from these power plants and run it over to people's houses. So if someone could figure out a way to actually transmit the heat, move it over miles and miles from the power plants into people's homes, we could just use the waste heat as actual heating for people's homes. And so this is another gaping hole, another very important problem that to try and solve if we can. So I'll stop there. Just quickly acknowledge the funding sources: NSF, ARPA-E, Solar Energy Technologies Office, and ONR. And I'd be happy to take any questions anyone has. And thanks for your time.
That was fantastic. Thank you very much. We do have a whole bunch of questions. I'll ask everyone to continue to put your questions in the chat. But maybe we can start off with Constantine. You had a question about cost-efficient batteries.
Oh, yeah, when lithium-ion batteries were mentioned, I was wondering, are cost-efficient alternatives being developed? Like, although it's not really a long-term thing, it's more short-term?
Yeah, so people are trying to push the cost of lithium-ion batteries down. There are a number of modifications people are looking at, and they're hoping to get down to $50 a kilowatt hour eventually. That may involve like recycled batteries and batteries that have a number of modifications to improve. But even $50 a kilowatt hour is actually not low enough. So there's some studies that have provided guidance and predictions on exactly how low in cost we have to get, and it's actually below $20 a kilowatt hour.
Thank you, that's helpful.
Thank you, great question.
Deval, you have a question about this energy storage?
Yeah, so my question was, would it be more efficient to just take the heat that the solar panels are using to convert to energy and just store that heat immediately instead of converting it to electricity and then back into heat? And why aren't people doing that? And is it due to just cost, efficiency?
Excellent question. So the short answer is yes, people are doing it. It's a different technology called concentrated solar power. And basically what you do there is instead of, like you said, instead of converting the light to electricity immediately when it hits the cells, instead of PV cells, what you use are mirrors. And so you reflect the light up to like a tower, and you convert the light to heat, and you have a high temperature heat source. Then they flow, usually it's molten salt, and they flow a salt through that receiver, which receives the light, and then they heat up the salt. And then you can store the salt in these giant tanks, and it's like a big thermal battery. And so that's actually in many ways where our concept came from, is because that technology's been out since the 80s. It's actually pioneered in the United States. So you get to this basic question, okay, well, why aren't we doing that? So a couple issues. One, that technology, the cost is not as competitive. So right now, that technology in the best places on the world is cheaper than PV plus lithium-ion batteries. So it actually is cheaper than that, to your point, because it's more efficient and a number of other things. The problem is that the only place it really works well is where you have what's called direct sunlight. You need a high DNI, direct normal incidence. That's like in deserts. You need basically no clouds, because what happens is the clouds scatter the light, and so they don't hit your mirror at the right angle to then get reflected up to the tower, so you end up losing a lot of the light. And so that's called diffuse light. That's one of the second issues it has. But there is an ongoing program at the Department of Energy trying to develop that technology and reduce its cost. Some of my work has been funded by that group, and so they're looking at a variety of alternatives to try and get the cost down. So it's definitely one of the contending technologies, but I don't think it's likely to win just because of it. Or let me say, I don't think it's likely to be a major part of the solution just because of the range of climates where it's most applicable and low cost.
Thank you very much.
Good questions. You're on mute, Jeff.
Thanks. Zaid, you had a question about preventing energy loss?
Yeah, so as you were talking, you were all like, the molten metal inside of these basically energy storage cells is like white hot. And so that got me thinking, like, how do you guys prevent the heat radiating out and the light radiating out to basically not go into your PV solar application, if you will?
Yeah, so the entire system is surrounded by thermal insulation. So the thermal insulation actually happens to also be made out of carbon. So it's porous carbon, and it's very thermally insulating. So the light is not, it's opaque, so the light can't get through it. But it's also insulation, so heat is gradually leaking through it. So there's a temperature gradient through the insulation. So we are continually losing heat to the environment. This is part of the reason, or the major reason, though, why it has to be large. So by making it huge helps us mitigate this issue. So to put it in context, the rate at which you lose the energy is proportional to the surface area of the storage unit. But the amount of energy you have stored is proportional to the volume. So as you increase the size, what happens is the volume is larger, it outgrows the surface area, so to speak. So the surface area to volume ratio gets smaller the bigger it is. And so what happens then is when you make something big, the rate at which the heat can leak out is small by comparison to how much energy you're storing. And so this is the same idea that happens in concentrated solar power. They make the plants very, very large. They make the storage units big. And so usually what happens is you make them sufficiently big where you only lose like 1% of the energy over the course of an entire day. So to give you a good example, there's a time constant. There's the time frame over which it takes for something to cool down is again related to this surface area to volume ratio. So if you've got a cup of coffee, for example, on your desk, the time constant for that is only like an hour. Like within an hour, it will cool down. When you make something like half the size of a football field, the time constant is months, meaning you could heat it up and it will stay hot for months. It takes months for it to cool down. And so we utilize that so that we could heat this up. And then, the next day you've only lost like 1% of the energy and you can go ahead and discharge the battery. And so the heat doesn't get a chance to leak out because it's just so large.
Okay, thank you very much.
Yep.
Okay, could we move on to Donning? You had a question about bioenergy?
Yeah, is there any potential or implications for using like biologically driven sources to store energy? Like I know cases like using algae and other organisms for biofuels, which is like a different context.
So this isn't necessarily my area, but I'll point out the kind of fundamental problem with biofuel related approaches is that at the end of the day, you're still using carbon as the carrier. And if you burn it, then you're going to make CO2. And so then the question is, how are you going to get the CO2 back? Well, the idea is that you've got to grow something that's going to eat the CO2 out of the air and then bring it back. So you end up being carbon neutral, but not necessarily not emitting the carbon in the first place. And, there are a number of people that are working on this kind of thing. It's promising in many respects. I think there are a lot of challenges in terms of cost and efficiency. But I think people are working on a variety of workarounds. It's not easy to make a reactor that's both, power dense and also cost effective. So you've got to get, let's say you've got some microorganism, you've got to get the CO2 into that microorganism. What people often do is they make like simulated reactors, right, where they're actually feeding it CO2. They're not feeding it air, and they're feeding it a concentrated stream of CO2. And they can make things that work very well. But then the question is, where do you get this concentrated stream of CO2 from? That presupposes that you captured and you pulled it out of the air. And that part alone on its own is already too expensive. So those are some of the challenges. I mean, if you can do it with plants and have it done essentially passively where the plants themselves are the ones grabbing it out of the air, that's also fine. But then you end up using up ginormous amounts of land area. And the ginormous amounts of land area are not actually a problem in the sense that we're going to run out of land. It's the fact that now, if you want to go collect all this biofuel, you need a robot that's going to roam a huge land area to go capture it. So it ends up spread out over a huge area. So these are just some of the trade-offs and complications with doing it. But at the end of the day, the question is, if you're going to burn a fuel with carbon and put CO2 in the air, the key question is, how do you get it back out?
Thank you.
Okay, Sarah, you had a question about superconducting materials?
Yeah, so I was wondering, what could be the applications of I know they're coming out with a lot of new ways to create superconducting metals with like reducing the heat to a level that you can like, yeah. And so there's that, and then I've also heard that heat extraction is also a thing that is commonly used. So I was wondering, is there a way to combine those two and also like apply this to like
Yeah, I mean,
energy transportation?
yeah, it would be nice to be able to use superconductors. A good colleague of mine, he was actually a part of one of the first superconducting companies called American Superconductor. I think he said he was employee number 5 at American Superconductor. So the way, let me first explain what a superconductor is and how it works. So a superconductor, as a good colleague of mine once said, is one of the only times in physics you'll get the closest thing you'll ever get to a free lunch. So it is basically a material whose resistance drops by so much that it's effectively no resistance. The reason this is important is because let's suppose you are making electricity in a desert somewhere and nobody lives in the desert. So now you got to move the electricity over to where the people are. When you now put up power lines to do that, those, there's current flow, and then the wires have resistance. So you're going to end up with heat dissipation. You're going to lose some of that energy as waste heat in those power lines. Turns out it's on average about like 7%. So you lose a significant little piece of the energy on the way. And so this prevents us from moving electricity over tremendously long distance. Like you wouldn't make electricity in Arizona and then ride it all the way up to New York. That's 1,000 miles or so. So what is nice and conceptually interesting about a superconductor is if you could have a wire that's lossless, that does not lose the energy, then you could think about possibly moving the energy from Arizona and gathering renewable energy in the places where it's most conducive, and then sending it where you want to use it, massive amounts of it over to other places that maybe the weather is not very conducive. So this is a technology that's constantly being developed. To my knowledge, it has not reached a level where it is cost effective enough to replace normal power lines, which don't have to be cooled. So keep in mind how these things generally have to be very cold. So they need like liquid nitrogen or liquid helium. And so that means you got to run a refrigerator to keep the thing cold in order for it to not have these losses. But then you got to pay for that cooling. So you have to put energy in, right? So at the end of the day, these are some of the challenges, but it is a very interesting prospect, particularly when you think about how is it that we are going to make the entire nation or the entire world carbon neutral. And there are definitely places on Earth where it's ideal to have renewable energy being captured. I mean, there are places that are very windy, there are places that are very sunny. And so if you can move the energy over great distances, then this would be, a big part of the solution.
Okay, Christian, you had a question about a concept for contained housing circuits. Would you like to ask?
Yeah, thank you. So not long ago, I learned about this water recycler. It's called Hydroloop. We actually take the water from the house, from showers and stuff like that, recycle. You can use it in house. I also learned about the Tesla batteries. So would it be easier just to try to make a house that is fully self-contained and recycle everything, so the heat that you actually generate either on the water here for the shower or on the dryer, things like that, can actually be recycled inside of the same house to keep the temperature control? And going back to the concept that you were talking about, transferring power through distance, would it be easier just to design a building that will generate its own power and it will be contained in the whole building, heat, power, water, and everything, and all this stuff, to reduce the carbon consumption on the transfer?
Yeah, I mean, from a conceptual standpoint, yes, those things are advantageous because they are kind of an elegant solution where everything's self-contained and you basically get rid of the wires. The problem and the reason that it often doesn't win out is because, let me go back to this point about surface area to volume ratio. it is very common that creating electricity, storing heat, many of these technologies have this kind of scaling issue where the bigger they are, the more efficient and the more cost effective they are. And that's why our utility grid has kind of optimized towards having giant power plants, and then you run the wires all the way around to everybody's house, because it's not very easy. Like if you scale down, so solar panels can scale down. So solar panels, you put one panel versus 100 panels, it's the same efficiency. So that's modular, it's not a big deal. But batteries, particularly the thermal battery that we're talking about creating as an example, very strong size dependence. If you had a turbine, very strong size dependence. So some of the things do not scale down well, meaning you pay such a huge penalty on both efficiency and cost trying to make it smaller. You're better off having a giant one somewhere that feeds lots of buildings. Now, in terms of wastewater or waste heat inside of a building, make an excellent point. And here's the challenge with it. Conceptually, yes, it makes sense. I had a good colleague, a good mentor of mine. He has a funny phrase, a funny saying, which is electricity is dirt cheap, so we treat it like dirt. The price we pay for electricity in the United States is so low. The price we pay for energy is so low that already to buy the energy from the grid, it makes it very, very difficult to make it cost effective to save the energy. So when you have waste heat, it's so low value, it's hard to make any piece of equipment that would scavenge that heat and reuse it, where it's not cheaper to just buy more energy because the energy is so cheap to begin with. So that's the hard problem we have, right? It's conceptually, yeah, we should save it, right? So we don't waste it, but it's actually cheaper to just buy some more. And this is kind of the problem that we have is the electricity price is so low. That's why it's so hard for renewables to beat it. It's because natural gas is cheap here.
Sananth, you had a question about the impact this work will have on future electricity use. This might be a great time for that.
So yeah, I just want to ask this question: how would your method of storing electricity through heat, how would that be the future? How would that impact future electricity use?
Ideally, it wouldn't impact the cost of electricity much if we can get the cost of our system low enough. What it would impact is the CO2 emissions from the electricity sector. So what we're trying to ultimately do, the most convenient solution is everybody just goes about their normal business, turning on their lights, turning on their air conditioners like nothing ever changed. And the difference is that we've changed the grid so that there's no CO2 emissions. And ideally, what would happen is once we can decarbonize the grid, you then try to decarbonize the transportation sector by having everyone switch to electric cars. So then when you charge your car, you're charging it from a grid that doesn't emit CO2. That also means we're going to have to expand the size of the grid. So we need more power from the grid to now power, you're going to have to get rid of all the gas stations. So there's no gas stations, and everybody's just either charging at home or charging somewhere else. And where does all that energy come from? It's going to be new power plants, and hopefully renewable power plants that are able to supply that energy on demand. The thing is, when do you want to charge your car? Well, you want to charge your car when you get home from work, and then it's in the evening and at night when the sun is down. So then where's all the electricity going to come from? Right. So hopefully it'll be this battery. Great question.
Great. Okay, there's maybe time for just one or two more questions. You had a question about nuclear power, Willie Chan?
Oh yeah. I'm just kind of curious about your as a expert. I'm just curious about your opinion on potentially using nuclear power, because I know some people believe in phasing it out, or not really relying on it too much because of safety risks. But with advancements that have currently been happening that make it more efficient and a lot more safe, I'm just curious about what your opinion, your take on this is.
My personal opinion is that the version of nuclear that we use today, I don't know that there's a version of how this all plays out where nuclear is the predominant solution. It'll be in the mix. There'll be some nuclear plants, but if you knew the details of how nuclear works and kind of how wasteful it is, people don't usually talk about this, but like when you have a nuclear fuel, they only use like 1% of the fuel's capacity before they throw it away. It's just that there's so much energy in it, they don't care. And, you know, we have this bad habit, and I think it's a conceptual problem, which is that we treat industries with as though like these environmental externalities will never matter because the earth is so big and we can just tolerate it, right? And so we mine for these materials, we use them to, you know, extract energy from them. And then what do? I mean, it'll kill you if you're around it. So we find somewhere to put it where no one's around. And we just hope no one day in the future will go dig it up. And you know, we make this hazardous waste. And this is precisely how we got in the situation we're in now. I mean, when people first started making engines, I was like, yeah, okay, there's CO2 going in the atmosphere, but the atmosphere is huge. It's ginormous. Well, you know, it'll never be a problem. And then it catches on. And the industry grows and grows to a point where now it's like, actually, all this CO2 we've been putting in the atmosphere is a problem. So I think, in my view, you know, the idea that we would put great stock in any technology, in any process that ultimately has an externality that we don't know how to deal with. We don't know what to do with the waste. We don't know. All we do is just lock it away somewhere. I think that's a problem. I think that mentality and that approach to making technologies is a problem. I do think that nuclear will play a role. I think that it's, you know, interestingly, I mean, like the specifications that they have to build to be able to build those plants are so grossly over designed. It's amazing, but yet and still, accidents find a way of happening. And nuclear accidents are, you know, essentially, you know, some of the worst accidents that can happen on the planet. And so to me, it's kind of like they're not going to save the day. And so the question is, you know, I think people should work on it, see if we can find a better way of doing it, but less risky somehow. But at the end of the day, I don't think that it's going to be the save all here or a huge part of the solution.
Okay, thanks. So the last question, I'd like to call on Chris Gu, who has a question about how to position themselves to tackle some of these problems. What should they be thinking about studying? So Christian, would you like to ask your question?
Yeah, that'd be awesome. Thanks so much, Professor Henry, for giving that very, very interesting talk. So my question is, if I were a freshman undergrad student, what kinds of subjects in STEM would I want to study to prepare me to research the solutions that you presented today, such as methane cracking and the heat battery solution?
So I would say mechanical engineering would probably be, you know, your ideal starting point. Also, possibly chemical engineering. You know, these are the two, and maybe material science. Those are the three main sub-disciplines of engineering that I think are tackling the most critical pieces of the puzzle. You know, I think electrical engineers are doing interesting things with software and some new hardware developments, but like mechanical engineering is really at the heart of the new hardware that has to be created to change the infrastructure. So, you know, a typical mechanical engineering curriculum is going to involve a number of things, statics, dynamics, mechanics and materials, design classes. And eventually when you get to probably your junior year, you'll take a class with me, like thermal fluids. And then you start getting exposed to heat transfer, fluid mechanics, thermodynamics. And that'll give you kind of the very basic foundation. I think this is another key piece I want to maybe mention to you all now. I've mentored lots of students. Many of them are very gung-ho about wanting to do something climate change related or sustainability related, and often come to the table or come and ask me for advice, and they're finishing up a bachelor's degree and they're trying to figure out, oh, well, what company can I go work for that's going to, you know, make a dent in this stuff. And the trouble with it is that there's a spectrum, and there are some companies that are very well established that are making some contributions and strides to this. However, if you're talking about the companies that are going to make all the difference in these things, they either don't exist yet, or they're startups, or they're early in their formation. And then the question becomes, okay, well, all right, I want to go work at one of these startups. All right, well, you have to think about what it is you can contribute. Many of these startups or earlier stage companies will not really be interested in hiring students with just bachelor's degrees. And the reason is because what they're doing is they're creating something from scratch. And so they kind of need people with more advanced knowledge than just bachelor's degrees. So you may, if you really want to be hands-on in the development of the technologies that will make a difference in the future, you will very likely need to go to graduate school and get some advanced degrees, some advanced training, so that you can go solve the harder problems for which there's no answer in the back of a book. That's the kind of training you'll need to really be able to think on your own, come up with your own ideas, go do research and develop them on your own and within teams. So you may want to definitely have it in your mind that you'll be considering going to graduate school.
Some awesome career advice. Thanks so much.
Thank you. Great question.
Okay, so thank you very much. This was a fantastic talk, and you can see the students are very, very interested. Lots of questions. We only got to probably a quarter of them. At this time, I'd like to introduce Daniel Wang and Miriam Brody. Would you guys like to present the shirt?
Yeah, hi. Thank you so much for your amazing talk on the physics of atomic vibration and grid scale energy storage and your technical advancements and your insights on that topic. So today, Daniel and I would like to present you with something.
Yeah, thank you for your talk, and especially the beginning talk with diversity, because I think that's a super important thing as well. And so on behalf of all the BWSI students, we'd like to present you a virtual t-shirt.
Thank you so much. I appreciate it.
Thank you.
Hi, thank you.
Thank you.
Thank you.
Thank you.
Thank you.